Hi folks, today we're going to talk about adiabatic processes. So let's put n moles of an ideal gas in a cylindrical container with an airtight piston on top of which we put some sand. Now the reason I'm using sand instead of weights is so that I can move small amounts of sand onto the piston and off the piston, thereby changing the pressure. See, the pressure of the gas, when the gas is in equilibrium, is given by the weight of the sand plus the weight of the piston divided by the cross-section area of the piston. So pressure multiplied by the area is the upward force exerted by the gas, which is balanced by the weight of the sand and the piston. Now what we are going to do is enclose this with a heat insulating material so that no heat can go in or out. So we have n moles of an ideal gas enclosed in this cylinder, and this cylinder is heat insulated so that no heat can go in or out. Now when we remove sand slowly, we are letting the gas expand with no heat going in or out. Such a process is called an adiabatic process. Or when we add sand, we are compressing the gas. That is also an adiabatic process. So during an adiabatic process, the heat supplied is equal to 0. During an infinitesimal part of the process, dq, the small amount of heat supplied, would be 0. And that, according to our first law, is equal to the change in the internal energy, the infinitesimal change in the internal energy, plus the work done by the gas, PdV. Now, what are we aiming for? We want to find the relationship between the pressure and the volume during an adiabatic process. For instance, when we add sand and let the gas compress, we know how the volume is changing. We want to find out how the pressure will change. So we have to get rid of du. So we substitute for du the expression NCV dt. Now if you don't remember this, I'm going to remind you of how we got here. Let's start with the property of any ideal gas, which is the internal energy is a function only of n, the number of moles, and T, the temperature in Kelvin. Now in this problem, and in most problems, n is fixed, which means the internal energy depends only on the temperature. So we need to find this function so that we can differentiate it and get this expression. Now, how do I find this function? How does the internal energy depend on the temperature? For this, we can choose any process whatsoever, measure the change in the temperature, find the change in the internal energy, and that way you know how the internal energy changes with the temperature. Now to this end, what we do is we'll choose an isochoric process. That means a constant volume process. Now for this constant volume process, dq, remember this, we are not doing the adiabatic now, we are doing a different process, a constant volume process, dq is equal to du plus pdv. But then, since it's a constant volume process, pdv is 0. This is the reason why I chose this process, because the change in the internal energy will simply be equal to the heat supplied, and that is very easy to measure. Now we know one thing, 1 over n dq by dt is nothing but the specific heat, molar specific heat. So this molar specific heat we are calculating at constant volume, so this is given called as, so this is Cv. According to this equation, it's also equal to 1 over n du by dt, from which you get du is equal to NCV dt. This tells us how the change in the internal energy depends on the change in the temperature. Now the beautiful thing is, this is going to remain the same. This expression is going to be valid for every process, not just the ones for which volume is held constant. Why? With different processes, the pressure will change, the volume will change, but the beautiful thing is the internal energy depends only on the temperature. And once we find through any process how the internal energy change depends on the temperature change, that will hold true for any other process. So let's take this and plug it in here. We are back to our adiabatic process. For our adiabatic process, we have NCV dt is equal to minus pdv. Have we achieved what we want to achieve? Nope. Because we want a relationship between pressure and volume as the process proceeds. But I have temperature here. So naturally we reach to PV is equal to nRT. Right? We want to eliminate temperature. So let's differentiate both sides because we have dt and dv and so forth. If I differentiate both sides, I get P dv plus V dp, that is the product rule, is equal to nR dt. Wonderful. I have n dt here, I have n dt here. So let's take it and substitute. So we get Cv multiplied by n dt. N dt is 1 over R times P dv plus V dp, right? Let's close brackets, is equal to minus P dv. By the way, where did this minus sign come from? I took du and took P dv to the other side. So du is ncv dt and P dv becomes minus P dv. Right. So let's put all the P dv terms and the V dp terms together. So we have V dp multiplied by Cv by R on the left side is equal to minus Cv by R times P dv goes that side, and there's already a minus P dv there. So minus 1 times P dv. Now check this out. I take the minus sign outside. What do I have? Cv plus R by R. But Cv plus R is Cp. Now from here, I'm going to go out here and write in yellow color. So we have, let's take the minus sign that side, minus Cv by R times V dp. Just for neatness, I took it that side. And out here I have Cv plus R by R. So that is equal to Cp by R P dv. Once again, we can further simplify this, cancel out R, and Cp by Cv is gamma. So we get minus V dp is equal to gamma P dv. Wonderful. This is a differential equation because it has got differentials, dp and dv. So when you are faced with a differential equation, you have to ask yourself, is this a separable equation? What does that mean? Now the variables are v and p. Can we bring all the p terms to one side and bring all the v terms to one side? Let's see. So we have dp minus dp, bring the p this side, is equal to gamma dv, bring v this side. Wonderful, we have achieved it. So the equation is separable. This is called a variable separable differential equation. And when you have that, you separate the variables and integrate both sides. So what is the left hand side? Minus natural log of p plus integration constant is equal to gamma times natural log of v plus integration constant. Let's bring both the integration constants together. We'll call it c prime. Right? Let me take c prime that side. I'll call it c. That is equal to gamma ln v, which is ln v to the power of gamma, and bring ln p that side, plus natural logarithm of p. Now you know that log a plus log b is log of a times b. So the right hand side is log of p v to the gamma, that is constant. So from this, we get the equation for an adiabatic process, which is p v power gamma is constant. Now how do we use this equation? When you have a process, you have an initial state with pressure P1, volume V1. You know gamma from whether it's a monatomic gas, diatomic gas, or a polyatomic gas. And since this quantity remains constant, if the final value of the pressure is P2 and the final volume is V2, we have P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma. Now let's go ahead and solve a couple of problems. So for our first problem, we have 2 moles of helium which are expanded adiabatically until the volume increases by a factor of 8. By what factor does the temperature change? Now we already have P v to the power of gamma remains constant along an adiabatic process. Now we want the relationship between volume and temperature, so we are going to use PV is equal to nRT because we are going to assume it's an ideal gas. And so we want to eliminate P, so P is going to be equal to nRT by V. So let's take that and substitute here. So we have nRT by V multiplied by V power gamma is a constant, which means since n and r are constants, T v to the power of gamma minus 1 remains constant during an adiabatic process. Now, we are told that it is helium. So specific heat at constant volume, molar specific heat for helium is 3 by 2 R. Let me quickly go over this. So according to the kinetic theory of gases, on average, the translational kinetic energy of any molecule is 3 by 2 kT. Now, helium is a monatomic gas. That means there is no vibration and there is no rotation, only translation. So this is the total energy on average per molecule, which is in fact a single atom because it's monatomic. So per mole you get by multiplying it with Avogadro number is 3 by 2 RT. This is the total internal energy. Now the internal energy is equal to number of moles, here it is 1 mole because we calculated it for 1 mole, N CV T. If I compare these two expressions, we get CV is equal to 3 by 2 R. And Cp therefore is Cv plus R, so it is 5 by 2 R. And lastly, gamma is Cp by Cv, so that is 5 by 3. So coming back to this equation, we have T v power gamma minus 1, 5 by 3 minus 1 is 2 by 3. That remains constant during the process. Let's say the initial temperature is T1, initial volume is V1 to the power of 2 by 3. It's equal to the final temperature T2 multiplied by the final volume, which is, according to our problem, 8 times V1 to the power of 2 by 3. Compare the two sides. You have 8 to the power of 2 by 3 here. 8 to the power of 1 by 3 is 2. 2 to the power of 2 is 4. So we have this is equal to 4 T2 V1 to the power of 2 by 3. So now, if you look at the left hand side and the right hand side, V to the power of 2 by 3 will cancel, and immediately we get T2 is going to be equal to T1 by 4. So by what factor does the temperature change? Answer 1 by 4. Our second problem is this. N moles of an ideal gas are expanded adiabatically, that's from A to B, from temperature T1 to temperature T2. So on a PV diagram, I have drawn two isotherms, T1 and T2, and this adiabat cuts across both of them. What is the work done by the gas from going from A to B? Normally, when we think of work done by a gas, we think of the area under the curve, and so we will integrate P dV, taking into account that PV to the power of gamma is constant along the adiabat. Instead, there is an easier way. Check this out. Along the adiabat, dq is 0. So that is equal to the change in the internal energy plus the work done P dV. Now, let me write this for the finite process A to B. So Q, the heat supplied, is 0, is equal to change in the internal energy plus the work done. Now we wish to calculate this quantity, so the work done is equal to minus change in the internal energy, which we can write as minus NCV delta T. Now we know CV for the gas. Let's assume it's helium. If it is helium, CV for helium is going to be 3 by 2 R. If it is oxygen, it is going to be 5 by 2 R. If it is methane, a polyatomic gas, it's going to be 6 by 2 R. So we know CV for this gas. So this is your answer, minus NCV delta T, which for our problem becomes minus NCV delta T is T2 minus T1, the change in the temperature. But T2 is less than T1, so T2 minus T1 is negative, so I can get rid of the minus sign and write it as NCV T1 minus T2. There's your answer. And that's it for this video, folks. Bye-bye. Until the next video.